In this video, we're going to talk about the method of moments, which is going to be an application of moment-generating functions for determining the distribution of another random variable, of a random variable that is a function. So this is a technique for determining the distribution of a random variable w, where w is a function h of x1, x2 up to xn, where especially this function is either a simple sum or a linear combination, and the x variables are mutually independent. So just a couple of comments before we go into looking at this method of moments and applying it in a couple cases. We have talked a bit about LOTUS, the law of the unconscious statistician. And this law lets us calculate expected value and variance and other moment-related things for our new variable w, but not probabilities for w. For that, we would need the distribution of w. And we saw a method, we saw in the single variable case, we saw a method of transformations for getting a distribution for a transformed random variable. And there is a multivariable analog to this, but we are not going to see it. So this method of moments is yet another way. It's not a method of transformations, but it is another method for determining a distribution of a function of random variables that works well in those specific circumstances we talked about just above here, where we have either a sum or in some cases a linear combination, and the variables are independent. So we're going to use two important results that we have seen about moment-generating functions and expectation. The first is that if the moment-generating functions of two random variables are equal, then those two random variables share the same distribution. So what we are going to do is for our unknown distribution w, we are going to find the moment-generating function of w, and we are going to recognize it. And if we recognize it, then we know the distribution that w must have. And secondly, we had this result about independent random variables x and y, that the expected value of a product of functions, g of x, h of y, is the expected value, the product of the expected value. So we're going to use both of these results here to calculate distributions, to figure out the distribution for a transformation of random variables in some very specific cases. So here's our first case. This proposition. If w is a simple sum, right, so this h of x1 to xn is just this simple sum. If this is a sum of variables x1 through xn, where those variables are mutually independent, and furthermore, if each of those variables is a Poisson random variable with parameters of the ith variable has parameter lambda I, then w itself also follows a Poisson distribution with parameter lambda of w that is the sum of the parameters of the x variables. So said sort of colloquially, the sum of independent Poisson random variables is also Poisson. So let's prove this. We're going to prove this using the method of moments, and we'll, for simplicity's sake, just do the case where there's only two variables, but there's nothing here that is particular about that. It just simplifies the notation. The same proof changed for n variables would work. So let's let x and y be independent, both as Poisson random variables, where the x has parameter lambda sub x, and the y has parameter lambda sub y. Now, we saw the moment-generating function of a Poisson random variable had a very specific formula. And so if we use for x with the parameter lambda sub x, the moment generating function was e to the lambda sub x times e to the t minus 1, right? So using the same moment generating function, because the distribution is also Poisson but with a different parameter. So the moment generating function for y is e to the lambda sub y times e to the t minus 1. So what we want to do is calculate the moment generating function for w and somehow relate it back to this form. If w is supposed to be Poisson, then its moment generating function should have the same form. That was the first bit of information up here. That's the first bit of information up here, that if there's only one form for a moment generating function for a given distribution. So if we let w be the sum of the two variables x plus y, and we go to calculate the moment generating function of w, by definition that is expected value of e to the tw, which is expected value of e to the t, w is x plus y. Right? This is a sum, so distribute that in and use the law of exponents, the expected value of e to the tx times e to the ty. And now we are using independence. In fact, in the previous lesson, we called this a property. We did all of these steps sort of in general without using any of the MGFs, and we came down to exactly this, that if w is a sum, that the moment generating for w is going to be the product of the moment generating functions for each of the random variables. So this part here, there's nothing new. We'd seen that already. What we are going to do that is new is this. We know those moment generating functions now for x and y. So the moment generating function for x is e to the lambda sub x times e to the t minus 1. Here's the moment generating function for y, the same form because they are both Poisson. And so now we know the moment generating function for w. We don't recognize it as anything yet, but if we clean this up a little bit, so first thing is I can use a law of exponents, and that's not cleaned up. I'm not sure what happened there. Let's be careful here and write this a little bit more cleanly. So using a law of exponents that have the same base, I can add the exponents. So we have lambda sub x times e to the t minus 1 plus lambda sub y times e to the t minus 1. And then using just a little bit of algebra, right? This factor is in common, so factor it out, and you end up by getting lambda sub x plus lambda sub y. But wait, hold your horses. Look at the form. Look at the form. This here, right, this here is sitting in front of the e to the t minus 1, so that means it is playing the role of a lambda. So if we say that if we replace this by lambda sub w, so lambda sub w is the sum of the lambdas, then we have exactly a Poisson moment generating function. And so the only way that a variable can have a Poisson moment generating function is if it has a Poisson distribution. So w must have a Poisson distribution, and its lambda, its parameter, must be the sum of the other two parameters. That is the method of moments. So let's go ahead and do the same thing one more time. And this time we're going to do it with normal random variables, and we're going to be a little more general because there is actually a stronger result for normal variables. So if w now is not just a simple sum, but it is a linear combination. It is a linear combination so that we can have coefficients in front of the variable. So again, I am thinking that this is the function of those random variables, right? W is a function of random variables x1 through xn, and it is a linear combination. where those x1 through xn are again mutually independent, and this time they're not Poisson random variables, this time they are normal random variables. So each of the x's follows a normal distribution with mean mu sub I and standard deviation sigma sub I. Then W itself is also normal. It follows a normal distribution with mean and standard deviation that are given by these expressions. So the mean of W is the same linear combination of the means of the component variables. So it is A1 mu1 plus A2 mu2 all the way up to AN mu n. And the standard deviation of W is this expression. It is the square root of the squares of the coefficients times the standard, or the variance, I guess, standard deviation squared. So A1 squared sigma squared all the way up to AN squared sigma sub n squared, and then square rooted to give you the standard deviation of W. So the common phrase for this is a linear combination of independent normal random variables is also normal. So we're going to do a proof again in the case n equals 2 to lighten up the calculation here. So we're going to let x and y be independent. Let x and y be independent and normal, so that x follows a normal distribution with mean mu sub x and standard deviation sigma sub x. Let y be a normal random variable with mean mu sub y and standard deviation sigma sub y. The normal moment generating functions are here. So we, in a previous lesson, looked at the normal for the moment generating function for a standard normal, and a standard normal, you know, has mu equal to 0 and sigma equal to 1. And if we plug those in here, if we were to plug mu equal to 0 and sigma equal to 1, we would get the result that we did for the standard normal, which was e to the 1/2 t squared. So this is the generalized moment generating function for a normal that you are going to show on one of your exercises. So I'm going to give it to you here without proof because you are going to prove it. You're going to base yourself on the standard normal and use that to derive both of these. Well, they're the same thing with the parameters changed. So here is the moment generating function for a normal random variable with mean mu sub x and standard deviation sigma sub x, and the same thing for y with the appropriate changes brought. Now, we are going to let W be a linear combination this time, right? With the Poisson random variable, we had a simple sum, so we had only the case where A equals 1 and B equals 1. That was for the Poisson, but for a normal, we can be more general. We can let any value of A and B be used in the linear combination. And then here now we have to be a little bit more careful because we do not just have a simple sum. So if we go through the derivation, we want to find the moment generating function for W, and again we are going to compare it to these forms up here and be able to make some deductions about the distribution of W. So the moment generating function is the expected value of e to the tw. That is the definition. W is ax plus by. So plug that in and then distribute the t. So we have e to the tax and e to the tby. Now again, law of exponents, split those up, and then independence tells us that we can factor the expected values. And now we're going to use a little trick that, well, it's not much of a trick, it's just true. But we haven't done this before, so I'm gonna explain it a little bit more carefully here, right? The moment generating function for x, right? This is by definition e to the expected value of e to the expected value of e to the t x. That is the definition. That is not what I have here. That is not what I have here. I have a little bit of something extra, don't I? I have TA times x, right? Whereas here I only have a t. Well, that's not really all that much of a problem if t is here and t is here, and what I want is ta. Well, then I'll just replace this t by ta, won't I? So I will say that the m sub x of ta is plug in ta in the place of t, and you get the expected value of e to the ta times x, which is what we have. So this being a little crafty in our usage of the moment generating functions, this is the moment generating function of x evaluated at ta, and this is m sub y at tb. So plugging those into exactly here. So for every t, I am plugging in ta for x, and for every t, I am plugging in tb for y. So there are the moment generating functions, and now it is just a matter of cleaning up a little bit. So if we clean that up a little bit, we can take the a out and put it in front of the mu, so it's a mu sub x. We can bring this guy in, right? The law of exponents, we have the same base, so we're adding the whole exponent together. We have tb, I can bring the b in front of the mu sub y, so b mu sub y times t. Same thing here, I can distribute the square and bring the a squared in front, so 1/2 a squared sigma squared x times t squared. Same thing here, so I get 1/2 b squared sigma sum y squared t squared. Now I bet you can see what is coming next. We have a t in two places, and we have a t squared in two places, so we are going to factor them out. Oops, almost gave away the surprise ending there. Well, it's no surprise, it's a theorem, we know what the conclusion is. We have the t here, right? Look, we have nothing but constants in front. We have the t squared here, again with nothing but constants in front. If we compare to the form of the normal moment generating function, we have something of the exact same form, except that we have a big long expression here where there is supposed to be a mu, and we've got a big long expression here where there is supposed to be a sigma squared, which means if we let that expression be mu sub w and this expression be sigma squared sub w, then we have got exactly the form of a normal moment generating function. And the only way that a variable can have the form of a normal moment generating function is if it follows a normal distribution. And so therefore w must follow a normal distribution with mu given as the linear combination of the means of the component variable, so a mu sub x plus b mu sub y, and standard deviation, well, if this is sigma squared, standard deviation is the square root of everything that's in here, so a squared sigma sub x squared plus b squared sigma sub y squared. Now there's one little thing to point out, and you are going to show this in your exercises as well. The statement that a linear combination of Poisson random variables is also Poisson is false. That was true for a simple sum, but false for a linear combination, right? If we can take a linear combination with the coefficients equal to 1, if all the coefficients equal 1, then we have a simple sum. So a sum of independent normal is normal. Well, there's two reasons why this is false. This should have said independent. It's false independent. It's false regardless because of the linear combination, but it was meant to say independent. That wasn't the reason that I meant it to be false. If you have a linear combination of normals, then also a sum of normals is a type of linear combination. It does not go backwards. So a sum of independent normals is normal, but a linear combination of Poisson, of independent Poisson, is not also Poisson. And you're going to show that for yourself.